So hello everybody, it's my big pleasure to introduce Pawel Dlotko today. Pawel is going to talk on the shape of data and relations. So please Pawel, the microphone is yours.
Thank you, Neja. Thank you to all the organizers of GEOTOP-A seminar. It's a great pleasure to be here. My only wish is that I could be in Mexico with you, but maybe another time. So today I'm going to talk about the shape of data and the relations, and that's a joint work with a bunch of people, with Davide, Anna, Simon, and Radmila. Some of the presented work is a part of all the work with Yongjin, Senia, Mohammed, Catherine, and Berend. And we'll be speaking about topological data analysis. And as you heard many times during this seminar, there's this credo that data has shape and shape has meaning. And TDA is using ideas from algebraic topology and then trying to integrate local principles into global invariants. And we have a bunch of working horses in topological data analysis. One of them is persistent homology, and I will not be talking too much about that, although persistent homology will appear at some point during the talk. And the other one is the mapper algorithm, and that's something I'm going to concentrate on today. So the typical pipeline of things we do in TDA, and yes, I think you can see my cursor. So we start from a data, which for the sake of that lecture, it will be either a point cloud or a discrete metric space in the form of distance matrix. Then we are using TDA to build some topological summary. And after this, we are applying on the top some statistical inference, machine learning, maybe just human-based interpretation, and we'll try to see all of those as we go. So let me focus on the main point, which I want to touch upon, which are the mapper type algorithms. So there's of course the conventional mapper algorithm, which by most of the people in TDA is just called the mapper algorithm. It's by Gunnar Fakonde and Gurjet from 2007. It's a state-of-the-art technique, very well recognized. Recently, I presented somewhat an alternative to it, which I call the ball mapper, and that we'll be speaking about this as well. And there are a few more possibilities to build mapper type graphs. But they all serve the same purpose, which is if we are given a high dimensional point cloud X, which is a finite point cloud, which is a subset of Rn, we want to first of all visualize the shape of that point cloud, and that's our first aim. And our second aim is to visualize a function on the top of this point cloud. So once we have a real value function f defined on the points of x, having values in real numbers, then we can also visualize this function using an appropriate coloration. So, well, if you want a short recipe how to use mapper, well, you need a point cloud. That's the first ingredient. And once you have a point cloud, you need to somehow construct an overlapping covering of that point cloud. And once the overlapping covering is provided, you are taking a one-dimensional nerve of that cover, and we call it a mapper graph, and that's a model of our space X. But then you can actually apply a coloration. So every element of the cover, you look at every single element of the cover, you compute an average value of your function f for this element, and that gives a value of a vertex in this mapper graph, and this value can be visualized using an appropriate color scale. So this way we can actually visualize functions from top-dimensional point clouds into real numbers. So let's take a look at this on an example. So if our point cloud happen to have a shape of a letter Y, what we want to do is to build an overlapping cover. Here's one of possible examples of such a cover. So cover elements are kind of enumerated with integers from 1 to 8. Just for the sake, I want to track them to vertices of the graph. And then I'm building a one-dimensional nerve. And what do I mean by that? Well, I'm essentially constructing an abstract graph, the vertices of which corresponds to elements of the cover. So there will be 8 vertices, and the edges corresponds to non-empty intersection of the elements of the cover. So for instance, if element of the cover number 1 have non-empty intersection with an element cover of number 2, then there will be an edge between a vertex 1 and 2. So here's this one-dimensional nerve. It's an abstract graph which I happen to visualize that way. And as we all can see, it kind of have the same shape as our initial data set. So it has a center plus 3 flares going out that center. In this case, this data kind of encapsulated the shape of our point cloud X. And now, as I mentioned, once we have the model of the space X, and if we have certain function defined on the top of the points. So think about it as the gene activity of some patients with some disease, and you want to look at the survival rate. So what I'm going to do is I will be looking at the survival rate for all the points which are covered by a vertex 1, compute an average, and that will give me a value of the function, of an induced function on the graph. And when I will do it for all the other cover elements, I'll get a function defined on the graph that can be visualized later with a proper color scale. So let me give you a real example of a situation where this can have been used, and I think that's one of the nicest examples we have in the TDA. So that's work by Bonica, Arnold, and Gunnar. When they looked at the breast cancer data set, so in this breast cancer data, they had they had a bunch of patients and the control group. They were kind of well balanced sets. And after some pre-processing, that they actually used what I call the conventional mapper algorithm that result in the graph which we can see on the screen. So the graph again have a shape of the letter Y. And then the coloration may be the survival rate, which is also available in the data set. It wasn't used in the construction of that of that graph. So what we can see is 3 branches. In one of the branches, this one over here, we happen to have control group. So a group of people who don't happen to have a breast cancer. The other 2 branches are the patients with breast cancer. The striking difference is that, well, in that branch, as you move further away, the disease is more severe, so the survival rate is unfortunately going lower. However, that branch over here, the branch sticking on the top, it's a branch of patients with the breast cancer with 100% survival. And that was discovered using TDA techniques on the dataset which was heavily explored before, using essentially all possible statistical methods. So in my opinion, it really shows the power of topology. So topology can discover something where other methods were not able to see, and that's also, in my opinion, of a clinical relevance. That's one of the examples how we can build a mapper. So essentially the pipeline was very easy. We start from a point cloud, we get an overlapping cover, we take a nerve, maybe apply a coloration. There's one more missing point, how to obtain the cover, and that's where the mapper algorithm kinds of are different from each other. Let me explain to you how this is done in the case of conventional mapper, and then we'll search for alternatives. So in terms of conventional mapper, I think it's worth mentioning that the motivation is coming from standard topology, namely from a concept of a REEB graph, which is defined as follows. So we have a manifold M, which in this case, in the example above, is a 2-dimensional torus standing up, and we have a Morse function defined on this manifold, Morse function with the value in R. And then we are defining an equivalence relation between 2 points, x and y in M. So we say that x is in relation with y, even only if the following 2 conditions are satisfied. And condition number 1 is that the value of f of x have to be the same as the value of f of y. In other words, they live on the same, x and y lives on the same fiber of f. But not only that, they need to live in the same connected component of that fiber, which is the second condition. So if we look at this example, and in this case, in the example above, my function is just a projection to the z-axis, also the last coordinate of a point. If I take a point in the range between here and there, then the fibers are just circles or a point at the top. So there is only one connected component of the fiber. There is one abstraction class. However, if I take points that have the value of the f between this value and that value, in that range, then the fibers are two circles, and therefore we have two abstraction classes, and symmetrically over here we have just one abstraction class. So a REEB graph is just our manifold quotient, the relation. And in case if f is a Morse function, by the work of REEB, we know that it will be one-dimensional graph, which is kind of visualized over here. And this conventional mapper is an attempt to mimic exactly this construction in case of M not being given to us as a continuous manifold, but as a finite sample of M. So right now, we still have a function from M to R, but it's only a function from a finite collection of points to the real line. Can we do something similar? And then how? And if you think about it for a second, I mean, asking for f of x equals f of y is not realistic. That will happen with probability 0. So we'll need to relax this condition a little bit. Speaking about connected components, if you have only a discrete point cloud, also doesn't make sense. So what you need to do is you probably want to look at the clusters of points instead of connected components. That would be the closest correspondence that we can figure out. And indeed, that was the main, an important idea in the construction by Gunnar Facundo and Gurjet. So instead of f of x equals f of y, we assume that they belong to the same element of the overlapping cover of the range of our function f. So this overlapping cover is kind of a parameter. I kind of have a freedom to choose how many intervals will cover the range of f and what will be the overlapping percentage. Bear with me, then it will be very easy to see why we need those overlapping intervals. So f of x will be considered close to f of y if their images will end up in the same element of the cover. So for instance, if I take a fiber over this element of the cover, it will contain those points and those points over here. Each of those points each pair of those points will be considered close. And then we have the second requirement about living in the same connected component of the fiber. Instead of connected components, we'll be speaking about clusters in the fibers. So that's another parameter of the mapper construction, a clustering algorithm. But I think we can agree that in that case, a reasonable clustering algorithm should tell us that there are two clusters. Here they are. For instance, if I look at the inverse image of this interval, there should be only one cluster, one abstraction class. But by doing so, by considering inverse images of those intervals, I'm constructing an overlapping cover. And well, this is what we need. Then we are taking one-dimensional nerve and we have a mapper. However, once you realized we need quite a few parameters to set up. So we need the number of intervals to cover the real line, the percentage of overlap, the clustering algorithm. What's more important, we need the function that actually maps our data set to real lines. So there are 4 parameters which we need to choose. And when thinking about mapper algorithm, I was thinking about a possible simpler way to construct this point cloud. This way depends on a single parameter epsilon. If a metric is given in our point cloud, and it's really based on a very simple geometrical concept, which is the epsilon net. So an epsilon net of x is any subset y, which is a subset of x, such that for every x in my initial set, there exists a point y in the subset, which is not further away than epsilon from x. Kind of a uniform up to epsilon distance subsample of x. But I can take the statement and turn it around by saying, well, if that's the case, then x is covered by the union of balls centered in the points of my epsilon net of the radius epsilon. So that gives me again an overlapping cover, and that's exactly what I'm looking for in the mapper construction. Well, let's take a look. So in the example which we already saw, the red points marked by arrows will be the elements of the epsilon net. And every element of the epsilon net, I will put a ball of the radius epsilon, I will get that cover. I construct a nerve, I'm getting something, well, maybe slightly different compared to mapper, but still this graph have the shape of the initial point cloud, and this time we are only choosing one parameter. Okay, so a few examples are coming, just to familiarize ourselves a little bit. This time I want to familiarize you with ball mapper, because I kind of assume that after almost 4 years of this seminar, you've seen quite a lot of mapper algorithms so far. And the first and my lucky example is the lucky cat. So probably if you ever been to a Chinatown, you saw it waving to you many times. And the idea of the experiment is as follows. I should mention no cat was harmed during the experiment. So we put our statue over here in the middle, and we are walking around with the camera taking different pictures of the lucky cat. So we see a front face, and then, once we are moving around, we see it from, I think that's the left side, then we see it from the back over here, from the right side, and we are coming back to the initial front face situation. Assume that we are taking low resolution pictures, so that those will be 128 times 128 pixels grayscale level. So every pixel really corresponds to a number between 0 and 255. Moreover, I don't want to look at this as pictures. I just want to, linearize them in any way. So just take the first row of the matrix and put the second row after it, the third row after it, etc., etc. And by doing so, every point have a value of the grayscale. By doing so, I'll get a point. Every image will give me a point in 16,384 dimensional space. The collection of all images will give me a point cloud. And the first question, I won't be asking questions this time, I will kind of answer it for you, is what is the shape of the point cloud? And then we can figure it out from the setup of experiment, obviously. Because once we start from a front-facing cat, that corresponds to a point. Once we move by a small angle, the image essentially is very close to the initial one. So we are moving on a trajectory a little bit away. But as we are, changing the angle, we are moving away by far, and eventually we are coming back from the other side. So when coming back, we are not backtracking; we are just coming back from another side. So our intuition tells us that this point cloud should be of the shape of a circle, and indeed we can load it to ball mapper, and that's the graph which we'll get. So we can make another observation. If we look at the degrees of vertices in this graph, then we'll realize that the vertices at the bottom have much higher degree than the vertices on the top. And the question is, well, why this is the case? And really what you can do, if you're lazy, you can just click on the vertices and then check which images are corresponding to it. But if you want to figure it out, it's kind of easy to say that the back of the cat don't have that many details. And therefore, in order to move a certain distance, you really need to move a considerable angle, and the front have much more details, and if you move by a small angle, you'll see a big difference. So that's the front of the cat on the top, and the bottom is the back of the cat. That's something we can get from this type of analysis almost. Another example is coming from UC Irvine dataset. That's a banknote authentication dataset. So what they are doing is they are looking at banknotes. Some of them are fake, some of them are real. And each banknote is assigned a vector of characteristic of the length of 13, if I remember correctly. So each banknote is represented by a point in 13-dimensional space. Over here, moreover, we know that some of the banknotes are fake and some of the banknotes are not. And we can use it as a coloring function. And in this case, the red points represent the real banknotes, those which are not fake, and the blue points represent the fake banknotes. And immediately we see that this point cloud have a shape of a letter Y. And probably there is something different between those fake banknotes and the fake banknotes over here. And indeed, if you look at the link and look at the paper, essentially, long story short, that they use two different printers to print the fake banknotes, which is something we're able to locate using TDA. So that's how we can use the coloration to actually make some discovery using TDA. I want to mention one more example, which is material science based. Again, work with Yonjin Senya, Mohammed, Catherine, and Berend. when we look at the databases of quite a lot of zeolites, those are nanoporous materials. So what we did, that's a nice example, by the way, because it can kind of combine persistent homology with mapper, which is not extremely typical. So every zeolite, we sample pores of this nanoporous structure. Using certain number of points, we have computed persistent homology, and then once we did it, we kind of look at the distances between those persistence diagrams, and we can take those distances and load it into multi-dimensional scaling, and it will tell us how the landscape of the persistence diagrams look like, and that's the mapper graph we obtained. The coloring is coming from the heat of absorption. That's something we can ignore at the moment. But what we realize is that different regions of those mapper graphs, which we called, group A, B, C, D, E, F, G, corresponds to different geometries of the porous materials. So if we actually click on the vertices in one group, we can see a kind of homogeneous geometry, which is different from vertices in other group. Those are just the geometry. Let me flash it for you. But that's an example how mapper algorithm can be used in combination with persistent homology using multi-dimensional scaling, and we'll come back to multi-dimensional scaling towards the end of the talk. Just speak a little bit about it. And kind of the main driving force for the development of mapper algorithms that I want to talk to you about today was the work with Radmila and Davide, in which we looked at the landscape of knots. What do I mean by that? Okay, so knot, as in knot theory, is simply an embedding of one-dimensional sphere up into three-dimensional space, up to isotopy. So, if two embeddings are equivalent by an isotopy, then we consider them the same knot. And for me, I'm not a knot theorist, not even close. Those are complicated objects to study, and people in knot theory were doing the same thing that we are doing in TDA, that they did it much before us. So once they have a complicated object, they try to assign some invariants, some descriptors to it, and hoping that those descriptors will tell them something interesting about the objects. In this case, I will focus on knot polynomials, like Alexander-Jones or Humphrey-Petit polynomial. I'll also speak a little bit about Khovanov homology, and we'll try to use the machinery of mapper to look at this. And I know in this seminar already Radmila was speaking about this research. She concentrated on knot theory. What I want to concentrate is the tools, the computational tools that can also be used for many different purposes except from the knot theory. So here we go. This is an example of Jones polynomial. And once we fix the basis of the polynomials, we use just the standard basis, preterm, t to power 1, t to power 2, etc., etc. Then we can get, then we can, every polynomial can get assigned a point cloud of coefficients in this particular basis. That's for Alexander and Jones. Let me mention that Humphrey-Petit and Khovanov homology can be interpreted as polynomials of two variables. So in this case, this is not really a linear structure, but an array of coefficients, and we can flatten this array into a vector, very much like we did in case of the lucky cat. So also in this case, those cases, we will assign a vector. It will be much longer because we are flattening a matrix to a polynomial of every node, which is attached to every node. So this way we are moving from knot invariants into point clouds, and that's precisely the situation in which we want to be if we want to use applied topology, in particular the mapper algorithms. So we can just take the point clouds coming from Jones polynomial and visualize it, and that's essentially the picture we'll get. The coloring is coming from the signature of the node, and of course the immediate question is, well, some of you may know that those tools are not really stable. We'll come back to this later. Question is what we see actually over there? And typical thing you do to check it is you are moving your parameters a little bit. There are kind of two types of parameters we can move over here. So first of all, we are looking at knot polynomials for all the knots up to a certain number of crossings. And we can increase the number of crossings from 15 over here in the upper left corner, 16 and 17 in the top row. So in the top row, we are looking at all the knots for 15, 16 and 17 crossings. Kind of see similar structure emerging. But then for the fixed number of crossings, we also have this parameter epsilon that we can vary. And we are varying it on the bottom row, and again, we see the same structure emerging over and over again. That gives us kind of hope that the structure is over there. That's, by the way, quite standard stability analysis that people do in practice in TDA. So we can take the data from Alexander polynomial, we can visualize it. This structure is a bit more boring, it's kind of linear, but then we can take different coloration and try to see how the coloring is distributed. So we can color by the norm, which in this case is just a norm of a point. You know, there are alternating or non-alternating nodes. We can color by this binary variable, and we realize that non-alternating nodes are kind of occupying the center, while alternating nodes are in the peripheries of the space of Alexander polynomials of nodes. We can color it by signature, and we don't see such a nice structure as we did see for John's polynomial. See there is a considerable delay. I hope you are able to see. We can color by signature mod 4, and you know, there's apparently, as Radmila told me, a folklore result saying that you know, the nodes that have signature mod 2 equals 0 that are in one side, and the signature mod 2 equals 1 at the other side, and we do see it in the mapper algorithm. So you know, then we can go and color, take KHOVANOV data and do the same business. Look at the stability, color it with, for instance, a signature. And we do see that KHOVANOV point cloud kind of discriminates signature pretty well, even better than the Jones point cloud. And that's all that we can do using standard mapper or ball mapper algorithm in this case. What I want to do is I want to take an inspiration from a knot theory to actually develop it further. So as I mentioned already, the mapper is a tool to visualize a shape of a point cloud X, but it's also a tool to visualize a function using the coloration. So let's take it further. How about visualizing functions from X to Y, where X is a subset of Rn and Y is a subset of Rm, and N and M are far away from 1, far larger than 1. So we have a map between two point clouds of higher dimension. Can we use mapper to visualize this map? That's the first question. Well, of course, quite likely X and Y will be something lower dimensional, so they will not occupy the whole space. And as an example, let's take a look at the map between the space of Alexander polynomials, which are embedded in 17-dimensional space, and the space of Jones polynomial, which are embedded into 51-dimensional space. We're speaking about nodes up to 16 or 17 crossings. Doesn't matter at the moment. If you want to play with this, there's a prototype implementation by Davide over that link. And of course, I'll send the slides later. So here's the idea, how to construct that map. Well, we are building a ball mapper of space of ball mapper or mapper space of Alexander and Jones polynomial separately. And then we are looking at a node, a vertex in Alexander polynomial. Covers a bunch of Alexander polynomials of nodes. We are asking which nodes are covered by that particular vertex. And then we ask where those nodes are located in the space of Jones polynomial. We can do it for a single vertex. We can do it for a collection of vertices. Nothing changes. So here's how it works. So we can just denote a bunch of vertices in the space of Alexander polynomial. We ask, okay, what are the nodes covered by them? Aha, here they are. So where they are located in the space of Jones polynomial? Well, we can see it by the coloration they are located. And then we can take the next section of the Alexander data and ask the same question, and then the next section, the next section, the next section, etc. And what we see is that as we move along the space of Alexander polynomial, we also move along in the space of Jones polynomial. However, the Jones polynomial seems to have, much more variety because we have this additional axis on which the things are happening. In other words, I really like to think about it as if, if I take a space of Jones polynomial, compress it in this direction, and I'm kind of getting the space of Alexander polynomial. It's not a rigorous statement, it's just an analogy. Okay? So, we can use mapper graphs to visualize maps between descriptors. In this way, it's pretty easy. The only important thing really is that, we have two descriptors of the same objects, in this case nodes. So we can ask, okay, which nodes are covered by this collection of points, where they are located in the space of the other descriptor. That's really all we need. And that's, by the way, quite a universal scheme that we can apply in various occasions, and I'll just provide a few examples later on. But then, when you are doing data analysis, you probably have already heard about this thing which is called the curse of dimensionality, which essentially means that the algorithms we have don't really work in high dimensions. Our intuitions don't really work in high dimensions. And well, the space of KHOVANOV, Hom-PT polynomials, they are reasonably high dimensional. Let's use them as the model of really high dimensional spaces. And let's see if we can use combination of mapper and ball mapper to enhance our understanding about very high dimensional point clouds, despite the curse of dimensionality phenomena which we see. So, what we can do. So there is this concentration of measure happening in high dimension, which really means that if you take an arbitrary couple of points, their distance will be the same regardless of the couple of points you are choosing. So essentially, all the points are the same distance away from each other. Building ball mapper in this case doesn't make real sense because for some small radii you will have just one vertex covered by a ball, and eventually there will be this threshold once you reach this average distance between points, and then everything will be just covered by one vertex. So that's not really informative. Perhaps you can use conventional mapper. Well, then we need this lens function, this function f that maps our point cloud, very high dimensional point cloud x into real line. And that's probably also not the best idea because with such a huge dimension reduction, you will lose a lot of information. So perhaps we could use mapper if we are able to project into kind of a medium dimension. But then the mapper construction gets into trouble. And here's why. Well, it really based on the covering of the range of our function with overlapping intervals or generalization of intervals, which are boxes. And the problem is that the size of those overlapping family of boxes is growing exponentially with the dimension. So if I have a covering with 5 boxes over here, if I want to do something similar in dimension 2, then I will need 5 square cubes, so 5 to the power of 3 in dimension 3, etc., etc. Not feasible, not practical. Question, can we do something about that? And so let me actually look at the setup in a bit more abstract way. So we have a projection f, which is a projection from Rn, uppercase n, meaning very high dimensions, to R to lowercase n, meaning, okay, medium dimension. So we have this relation. I wrote that it minimizes some sort of entropy. That's really not necessary over here. So what we can do? Well, in principle, we can look at the image and apply our techniques there, but that's not entirely, that do not entirely satisfy us because we are losing all the information about the fiber of f. And, well, is there an alternative? Of course it is, otherwise I wouldn't be asking this question. If we take f of x, which is the image of this point cloud in the medium-sized dimension, we can construct a ball mapper of f of x, f of uppercase x, and what you need to realize is that ball mapper is nothing more than an overlapping cover of the input, in this case f of x, and it's really adaptive. So it's covering the point cloud, but nothing more. And therefore, we don't have this problem of exponential explosion of the coverage of the range. We can just use ball mapper and use as many balls as it takes, but we have an adaptive cover of f of x. And then we can do exactly the construction of the mapper. So for every cover element, we look at the fiber above it, we look how many connected components they are, we build an overlapping cover in very high dimensional space, and we construct a standard mapper over there. Let's take a look at an example. In this case, it's very difficult to plot a reasonable example because I cannot plot in very high dimensional space. I cannot even plot in the medium dimensional space. I can only plot in two-dimensional space, and therefore the example is kind of maybe a bit artificial, but I hope it will serve the purpose. So we have this star shape having 6 arms, and we want to map it to the star shape containing 3 arms. And the mapping goes as follows. So the points from arm number 1 and the points of arm number 2, they mapped to the points in this arm number 7. So they're mapped in order, right? So this point and that point is mapped to the point over here roughly. And likewise, points from arm number 3 and points from arm number 4 are mapped to the arm number 8 over here, and the points from 5 and 6 are mapped to 9. So that's our mapping between the very high dimensional space, or at least our model of it, to the medium dimensional space. So what we are doing right now, we are building a ball mapper graph on the thing on the right. Here it is. And now we are looking at the fibers. So let's take a look one by one. So the ball A, the inverse image is just a smaller star. One connected component, nothing too fancy. If you look at the ball F, well, the inverse image will be over here and over there. We may hope that a reasonable clustering algorithm will tell us two connected components. Likewise for D, likewise for B, likewise for G, likewise for E, likewise for C, we have the inverse image will contain two connected components, and the mapper graph constructed on the top of ball mapper graph will really be, the shape we started from. That's just a mapper graph. Ball mapper graph we started from. So using mapper on the top of ball mapper, we can not only project the data to the medium dimensions and hoping not to lose too many information, but we can also recover the information about the fibers of this projection. I think that may make a difference. So in the context of node data, we have a spaces of Alexander and Jones polynomial. We already solved this. We have a space of Homfly-PT polynomial, and we know that Homfly-PT restrict to Jones and to Alexander using this relation. So if we replace the first variable by t2 minus 1 and the second variable by the square root of t minus 1 over square root of t, then from Homfly-PT polynomial we recover the Jones polynomial. And there's a similar projection for in case of Alexander polynomial. Nevertheless, we can use those as the projections from very high dimensional space into medium dimensional space. And we can look at the fibers and see if something comes out. So let's say in the interest of time, I won't comment too much about those plots. Radmila did it already in her talk, but we can see things that we haven't saw on the ball mapper graphs of Homfly-PT or Jones or Alexander polynomials. And that may be interesting from a perspective of not theorists. Okay. And there's one more thing that knot theory is inspiring us to do, namely the symmetries. So the space of Jones polynomials admits certain symmetries. So if we take a Jones polynomial of a knot K and the Jones polynomial of the mirror knot, there is a relation between them. It really corresponds to a symmetry across the origin. So our point cloud is symmetric across the origin. Our graph is not. And this is because we didn't pay attention when building the graph for the symmetries. And we should pay attention, and we can pay attention for it. And this is how we do it. And in case of ball mapper, the way to proceed is kind of easy. So let me actually formulate it in a more abstract, general way. So we have a group G acting on a point cloud X, and we want to have the same group acting on the mapper graph on X. So if there is a symmetry, for every vertex there should be a symmetric vertex, so that the G action is mapping nodes covered by that vertex to nodes covered by this vertex. How we do it? Recipe is very simple. If you select a landmark point, so a point from your epsilon net, as I call it, to the ball mapper graph, you add the whole orbit according to G of that point. So instead of adding one point, you are adding the whole orbit according to G. And then it's quite easy to verify that, well, the action of G is actually repeated, it's actually shadowed in the ball mapper graph. So that's a ball mapper graph, already equivariant ball mapper graph obtained on the space of Jones data. And we see those symmetries, which are not exactly visualizing the plotting. It's because of the plotting subroutine we are using, but we can explicitly and rigorously write down how the map G is working, how the map G is acting on that particular graph. And this graph is also symmetric. You can see it, you can trust me, you can look at the paper. The proof is straightforward in this case. So we can adapt those tools of TDA to actually taking care of the group actions, taking care of the symmetry. Let me indicate that this method is much more general than just the knot theory. So the knot theory is a great inspiration, is a great playground for tools. But those tools then can be taken and transferred to different fields. This is what we are doing. This is what I would encourage you to do. Let me just give you one example. Material science, zeolites, something that we have already mentioned. There are multiple descriptors to characterize zeolites. There are conventional descriptors. Just put a list of them, so just a bunch of numbers that characterize every single material. There are TDA-based descriptors based on persistent homology. Question how they relate to each other. And it's the same question how Alexander polynomial relates to Jones polynomial. And we can try to answer it using the same tools. Is the relation between them? I don't know at the moment, but the results are coming. If you are doing machine learning, artificial intelligence, encoder-decoder type architectures, for instance, I showed to you this mapper plot obtained by taking the first coordinate of multidimensional scaling. Why only first? Well, taking the first is a restriction of mapper algorithm. But with mapper on the ball mapper, we can take as many as we wish. The question is, will we get a different picture at some point? Perhaps we can recover more detailed information by taking projections on higher dimensional space. Excuse me. And, even when looking at encoder-decoder type applications and trying to understand the projection, the same technology can be used. And that's something we are looking at the moment. However, to answer these questions, so let's take let's fix on the question of multidimensional scaling. Should I take 1, 2, 3, 4, 5 coordinates of the multidimensional scaling? How can I decide? Well, I can just take those projections and visually compare the graphs and see what convinced me best. But that's not entirely something that, well, it really depends on my perception. And that's something we want to avoid. We want to have some algorithmic tools that actually can do a rigorous analysis. Can we do it? Yes, we can. And that will be the last point in my lecture, so I think I have 5 minutes, that should be enough. But the same tool, so I'm speaking really about a way to defining distances between mapper graphs. It also can be used to somehow help with lack of stability of those graphs. So mapper algorithm is known to be unstable. What does it mean? Well, small change in parameter may result in totally different graphs, whatever it means. Questions studied by many, just to name Liz, Yusu, Steve, and Matthew, just to name the few. So in order to believe that the structure returned by mapper is really there. What we do is we typically allow to manipulate our parameters a little bit and visually inspect if the obtained graph are similar. That's what we do. We already saw it in the case of node data. Ball mapper is also non-stable, and it's really because distance function is not stable in a sense. So what we can do is we can select different parameters from a certain range and do a bootstrap and see how many essentially different mapper graphs are coming out. But in order to rigorously quantify what I mean by essentially different, I need to be able to compare mapper graphs. And this is how we can do it. And that's my suggestion. Again, that question has been studied already by a bunch of people. And they were looking at isomorphism or homeomorphisms between graphs. What I think is important is to relate those graphs to the data that they're covering. And this is how we are doing. And it's okay, not yet. So before we go over there, let me mention the instability provided by Steve and Matthew. So over here they just look at the two parameters, the number of overlapping intervals and the percentage of overlap, and they realize that once you move those parameters a little bit left or right, then you get a structure that is blinking unstable. Mapper graph. If we build a ball mapper graph on 5 points, depending on the selection of landmarks, if you select the first, the middle, and the last, we get a graph like this. If we select the second and the last but one, we get a graph like this. If you select the second and the last, we get a graph like this. Those are quite different graphs, but they do have something in common. They are covering exactly the same points. So I know where the points covered by vertex 2 over here are in the first graph and in the second graph. And I can use it to my advantage to define the distance. I just want to check, Neja, can I go for 4 more minutes? Maybe 5? Good? Okay.
No problem.
Okay. So we have graphs, but they're covering certain points. That's very important. So for instance, over here we have a point cloud of a circle which is kind of not enough. There are not enough sampled in this region. Depending on the selection of landmarks, we may get either a closed circle, not closed circle. The point is that the points covered by that vertex will be the points covered by that ball, and the points covered by this vertex will be roughly the points covered by that ball. They're quite close to each other. Likewise for this vertex and that ball, this vertex and that ball. What makes those two graphs different is that in this graph, the points which are close in this graph are far away in the other graph. So it means that there is really some lack of continuity over there. That's the main idea I want to utilize over here. So I want to take two mapper graphs in general, G1, G2. They're constructed on the same set X. And for every vertex of G1, and then we'll do symmetrically for every vertex of G2, we assign a map from vertices to G2 to 0, 1 in the following way. So let me take a vertex 2. It contains, this vertex, that vertex. It covers this point, and that point. Where are those points in the second graph? Well, those two are here, and this guy is over here. So I have a map which, 2/3 of the mass of the vertex 2 is in that vertex, 1/3 of the mass is in the other vertex. So I know how those points covered by the same vertex in G1, this one, are where they are present in G2. And the fact that those things sum up to 1 is a coincidence because there is no edge between them. So in general, this is not a probability distribution, but it will be some function on the top of vertices. And I want to use those functions. I want to take two mapper graphs. For every vertex from the first one, I have this map. And I can build a bottleneck-inspired distance by saying, okay, what is the maximal diameter of the subgraph induced by non-zero values of that function? I'm looking at all the vertices for which f of v is not zero. I'm looking at the diameter of the subgraph. I'm checking what is the maximal diameter. That's an analog of a bottleneck distance. Once we have a bottleneck, of course, the question is, can we have an analog of Wasserstein? Of course we can. For instance, we can ask the question, if I take this fv, what is the total amount of mass I need to move to a certain point in order to compress, the subgraph induced by that vertex into a single point. It gives us an analogous of the Wasserstein distance. So I went a bit quickly through this. Tests are underway, but I think that's a nice way to compare mapper graphs, to do a bootstrap over mapper graphs, and do all the other things that you can do. So kind of wrapping up the whole talk, what we are trying to do is to extend mapper construction by using more mapper. That should be a fewer parameters, so we don't have that many knobs to turn. Parallel changes to see a ghost in the data, and really, if you have too many knobs, then you can see no ghost in the data, and don't have time to speak about that. But essentially, you can get an almost arbitrary graph if you are creative enough. Mapper of the ball mapper to analyze very high dimensional data. Equivariant mappers to analyze data with a certain symmetry. And the way to compare mapper graphs to be able to do bootstrap. Some of the implementations are already available. Look at my center webpage. It will be 2 slides below. Or some of them will be available soon. Just let me know. Use it, try it. Tell us if you like it. If you have any suggestions, I would be very happy to hear them. And I want to use last minute to make a private announcement, which is this Applied Topology in Band-Level conference. I know some of you have already registered, which makes me very happy. For those of you who did not, consider coming to Poland. We are organizing this event. In general, it's not only TDA, it's a much broader applied topology. And without losing too much time on the private announcement, let me thank you very much for your attention. I'm happy to answer any questions you have. Thank you.
So thank you very much for this really very, very interesting talk, Pawel. I would like to add that the venue of this conference that you were just talking about is a beautiful place, so I encourage anybody to go. It's very, very nice, and usually the company is great. So do we have any questions, please?
Great company is guaranteed.
I think Massimo has a question.
Yes, I have one. I don't know whether it is a question or a proposal, Pawel. I was fascinated by the knot theory thing. And I thought of this. I remember that there are some incomplete invariants for knots, meaning that they are invariants of knot diagrams, but they do not pass through all Reidemeister moves. Okay, and generally they are either a step inside the construction of a true invariant, or they are useless at all. I think they might be very useful for doing a similar thing to what you explained, meaning not taking many knots, but just taking one knot type, taking all the diagrams within a certain number of crossings, say, and looking at the space of those incomplete invariants of the diagrams. I mean, they must be incomplete, otherwise they would just have one invariant, okay? But having many for the same knot, and I think it might be very interesting to see what the mapper construction does in that case for a knot, and say a knot which is not too different, but how do you think? Question, has anybody done something like that? Proposal. If nobody did, it could be a nice thing to try.
Hi, maybe if I can try to...
Yeah, yes, go ahead, Radmila. Or Neža, I'm not sure who was speaking.
Yeah, I did say...
Radmila, please go ahead.
Hi. So this is a hi. I'm
Thank you for saving me, because I didn't know how to answer this.
It's a very curious proposal. I'm just not sure what kind of almost invariants do you have in mind, because the only ones I'm aware of are maybe invariants of so-called ribbon knots, right? Where you, for example, don't have a Reidemeister 1 move, So, for example, Lu's version of the Kaufman polynomial is one of those that doesn't satisfy R1 necessarily.
Yes, exactly. I was thinking of some work of by Lou Kaufman with some invariants which he had to sort of correct for not passing through a Reidemeister move. Okay, but generally, if you have something which you can make into a vector and which generally one could not think as useful because it does not pass through all moves, it might be interesting for looking at the space of those pseudo-invariants of diagrams for a single knot type. Do you think so, Radmila?
Yeah, so it's very interesting. Again, I would love to, if you have any suggestions for other invariants, I would be happy to look at. But the thing is that even with knot invariants, they're all computable knot invariants are imperfect, right? So they all fail to distinguish some knots. So one of the great things about the collaboration with Pawel and Davide was that this approach offered, I think, I don't want to sound, that we're doing something amazing and that Noah has done, but the sort of comparison between knots and links sort of knot and link invariants amounts to kind of either specializations or like kind of they're on a case-by-case basis. So this was the first time that someone had done maybe even kind of a statistical, maybe not the first time, but kind of first systematic attempt to compare the strengths of these invariants and what they're telling us in a kind of more global way. But again, I'm curious to sort of know which other almost invariants we can use. So great idea.
Maybe we should try to arrange a three-way call at some point, so sometime in the future to actually discuss it in details.
Mm-hmm.
Thank you. Anyway, great. I loved that very, very much.
Yeah. Thank you so much, Massimo. And I'll send you an email to you and Radmila, and we can arrange some conversation.
Okay, so sorry, go ahead, Radmila.
No, if I may say, if anyone has any invariants of not necessarily knots, but any sort of topological invariants, it would be interesting that are computable for like a fairly large number of things, then maybe this is your toy to play with. Thank you.
Yeah, that's our setup, exactly.
Okay, well, thanks very much. Do we have any more questions, please?
So one more question.
Yes, please.
So very, very nice talk. And going back to your ball mapper graphs of Alexander and Jones, do you have any idea why this dispersion between the two graphs corresponding to the invariants? I mean, this one.
So why this? I understand the question.
I mean, the Jones polynomial invariant seems quite more dispersed than the Alexander's. Is there any explanation for this, or I mean topological, or maybe the way you are graphing these two?
That's a great question. Again, I'm not a knot theorist. Radmila, do you have any intuition why it may be that Alexander polynomial seems to be lower dimensional than Jones, which is I think what the question is about? I am not aware of any intuition. I mean, it's purely data-driven observation, and maybe Radmila will be able to answer the question, but from my perspective, that's a great observation. And the question why in knot theory, the attempt to answer this question should follow up. And this is where TDA can be applied to a pure math, leading to developments of new theorems. But what are those? I have absolutely no idea. Radmila?
So, thank you for the great question. We actually, in a different project, we actually studied something that could be kind of thought of as a dimension of this data set, and then Pawel has a follow-up project. that indeed kind of suggests that the Jones polynomial has dimension 2 or even 3, and the Alexander polynomial is one-dimensional. Why? I have no idea, but I just want to offer like this one piece of insight that in general, when you're talking about the Alexander polynomial, it comes, of course, from the Alexander module and so on and so on. So it has like true topological interpretation, right? Where the Jones polynomial comes from operator theory or representation theory, and it's sort of, at least in its origin, it's less topological. However, when you compare them on the level of polynomials, again, the things are just, oh, if we plug in 0 or 1 or whatever, you get some similarities. However, when you look at their categorifications, which Pawel briefly mentioned, so Jones polynomial is categorized by the Khovanov homology, and the Alexander polynomial is categorized by so-called knot-floor homology, or various versions of it. There's an amazing result that we don't see here, and actually cannot be, between homology theories that cannot be downgraded to the polynomials, that actually says there is a spectral sequence between Khovanov homology, from Khovanov homology to knot-floor homology. This spectral sequence construction suggests that there's only a loss of information along the way. So in some ways, Khovanov homology should know everything that knot-floor homology knows. And knot-floor homology has amazing applications in actually detecting properties of knots in 3- and 4-dimensional manifolds. But Khovanov homology, not so much. So what I'm actually looking at here is that maybe can we actually compare the actual strengths of these things? Okay, it appears 2-dimensional, this appears 1-dimensional. But again, we are interested in them not as just polynomials, but like what kind of topological properties of knots they actually know about. So in that sense, maybe this 1-dimensional structure of Alexander polynomial is all we can get. I doubt it. But again, somehow the Alexander polynomial and their categorifications and its categorifications are have much richer applications than Khovanov homology and the Jones polynomial when it comes to topological properties of knots. So that's something that I was looking for. And then again, the thing that we're looking at with Pawel is that home-fly-PT polynomial actually specializes to both Alexander and Jones. And then one thing that maybe ball mapper can be used for is to sort of, because it combines the data, right, from both Alexander and the Jones polynomial, to sort of see, are they overlapping, are they orthogonal? Like what's the span of the knowledge of the home-fly-PT polynomial? I apologize for the long, we're over time. I'll stop here and I'll be happy to talk.
No, thank you.
For the questions and answers. We have some questions on the chat. So there is a question here, can we talk of a groupoid? So maybe the author of the question should ask. No reason for me to read. Please.
Yeah, I'm trying to find the... oh, here's the chat.
So please, Ananta Krishna.
Hello, am I audible?
Yes. Please go ahead. We can hear you.
Yeah, I was wondering, like, since we can talk about like equivariant mappers, can we also talk about something like where you have some kind of groupoid like action on your space, and then can you talk of a mapper for that?
Pawel or Radmila?
Yeah, I don't see why not. In principle. But yeah, I think in principle, because at least for the ball mapper, the idea is to, along with a landmark point, it really boils down to the simple observation that if the group action is an isometry, then once you add along with a landmark point the whole orbit, everything goes correctly. But I don't see in principle a reason why not. But that would require some better thinking. I mean, in principle, I don't see a reason why not. That's the only answer I can give right now.
It seems like a good idea for further work. So do we have any more questions, please?
There was the other one that I asked at the top also. Can you associate a measure of similarity between the same mapper graph based on different colorations?
Oh, so you also want to incorporate the coloration into...
Yeah.
Okay, because we are only looking at the structure so far. So if we add a coloration in the game, I mean, in principle, again, yes, I think we can. In reality, because quite typically, what we see in practice is if you take a vertex of one graph, kind of distributed in a certain region of another graph, but it's overlapping with another vertices on a small percentage of points. And what we can do reasonably is to try to compare the coloration of the graph we started from with the coloration of the whole subgraph. But then, because of such a small contribution to certain vertices at least of the other graph, this comparison may not make sense.
So we have an answer
So again, in
here.
principle we can. In principle we can, but I'm not sure if it will be any meaningful because of the observations we have at the moment.
Thanks.
We have an answer by
Welcome.
Radmila here. Obviously, one of your students is working on this, Radmila. Is that correct?
Yeah, that was the question about applying this thing to the. No, it was a different thing. So thank you. Yeah.
I think it was Massimo's question because it's already a few minutes ago.
Okay. So do we have any more questions, please? Well, if not, let me thank Pawel again warmly for this very nice talk, and also Radmila for her contributions. And this is very, very interesting work with obviously a lot of possibilities for further work. So thanks very much.
Thank you so much. And if you have any further questions, please feel free to contact me. Otherwise, have a great day, have a great evening in beautiful places in Mexico. All the best, and talk to you soon.